Okay, so thanks everyone for attending today's talk. So our AI seminar talk today is by Tyler Hayes. And I just want to express like how excited I am to have Tyler here today. So briefly about Tyler. Tyler is a recent PhD graduate from the Rochester Institute of Technology, did PhD with Christopher Cannon. And she is an expert in online continual lifelong machine learning. So by looking at her work, we can tell that she focuses almost exclusively on this area and its related problems such as catastrophic forgetting. And my own group is excited to see her work, especially on the biological plausibility of some of our computational mechanisms. We are also excited to see her work on online continual learning under resource constraints, such as on embedded devices, which entails like being worried about resource hungry approaches, such as using large replay buffers or expensive batch updates. My students and I are truly inspired by her work. So thank you, Tyler, for being here today to give an AI seminar talk to us. And it's all yours.
Thank you so much for the wonderful introduction, Rupam, and thank you all for inviting me today. I'm really excited to be here and talking about my research. Let me go ahead and share my screen. Great. So as mentioned before, if you have any questions during the presentation, feel free to interrupt me. Sometimes it makes for a better discussion anyways if we don't hold the questions until the end, but also if you want to hold it till the end, that's completely okay too. So I'm Tyler Hayes. I recently defended, oh, can you see my screen? Okay, great. Sorry, I just got a notification. Okay. So yeah, I'm Tyler Hayes. I recently defended my PhD at the Rochester Institute of Technology in Rochester, New York. The bulk of my research is focused on online continual learning. So today I'm pleased to present my research, Efficient Lifelong Machine Learning and Deep Neural Networks. So let's start off by talking about the traditional supervised machine learning paradigm. We take a data set and we split it into some different sets, perhaps a training set and a test set that follow the same underlying data distribution. We can then train the system in an offline way on this static training set. If we're using something like a deep neural network, this means looping through the data many times, shuffling it as we go through to make sure that the network understands the classes that we're trying to learn. We can then perform a separate testing phase where we provide the agent with unknown images and hopefully it would be able to correctly classify these. If the performance looks good, then we would say, all right, our system is ready to go, let's deploy it. But what happens when we obtain more data? This paradigm isn't really fit for that specific scenario. And this is where continual learning comes in. So continual learning in its most general sense means that we're going to update the network as new data becomes available. This means that we have an evolving training set that more closely resembles the natural world, right? We as humans aren't learning from a fixed static training data set. The world around us is constantly changing, it's constantly evolving, and we would like to update our knowledge as we are experiencing more things from our lifetimes. This could also be related to how maybe a robotic agent has a video camera on board and it's collecting visual frames, and it would like to be able to process those in real time as they become available. The biggest thing to note here is that the inputs are typically not independent and identically distributed, right? There's perhaps temporal correlations or some other type of correlation based on the way that the tasks are actually being defined. And so violating these assumptions typically has detrimental effects on things like convolutional or deep neural networks. Specifically, you might be asking yourself, well, if new data becomes available, why can't I just fine tune my network on that new data? So naively updating a conventional neural network on new data doesn't work. It actually results in what is known as catastrophic forgetting. So catastrophic forgetting is basically the abrupt loss of knowledge that the network once knew how to or tasks that it once knew how to perform in favor of being able to work well on new data. And this can become especially severe when your data stream is ordered in a specific way. So for instance, if I ordered my data stream by class, right, on the right-hand side, I'm showing you an example of what would happen if I took the Cub 200 bird classification data set and required a neural network to learn the classes one at a time. So basically, maybe it learns a blue jay category and then owls and then some other type of bird. And what you can see is this black dashed line at the top is representing the offline performance that I would expect if I were to train the neural network on a static training data set consisting of all of the images. It can loop through it and shuffle. However, if I just take a multi-layer perceptron network, which is shown in yellow, and I fine tune it only on the new data as it becomes available, we can see that the performance is catastrophic, right? It's catastrophically forgetting all of the classes that it once knew, and it's actually ending up around chance performance. So this isn't great. This means that we have to do something more intelligent in order to be able to overcome this problem. You might be asking, why does this catastrophic forgetting problem occur? This was first discovered in 1989 by McCloskey and Cohen, and it's as a result of what is known as the stability plasticity dilemma, right? In a neural network, we need to have stability in order to preserve previously known knowledge, right? If my network once knew how to do something, I need to keep the representation stable in some sense so that it can still perform well on that data. But I also need my network to be plastic enough so that it can acquire new knowledge. If I kept my representations fixed, it wouldn't be able to adapt to new information. So basically, to overcome this catastrophic forgetting problem, the network basically needs to be able to maintain a balance between stability of remembering old information and plasticity to acquire new information. On the opposite end of the fine-tuning spectrum, we have what I call cumulative replay, which can overcome the catastrophic forgetting problem. Cumulative replay is this solution where basically we can maintain all of the previous data that the network has ever seen in some type of database. When our new data becomes available, we basically mix all of the new and old data together, and then we can fine-tune the neural network. In a 2019 paper, we actually showed that with respect to an offline baseline, cumulative replay shown in black actually overcomes 99% of the performance that the offline model was able to achieve across various data sets and data orderings. So this is great, but as you can imagine, it has its own problems, right? Maybe it overcomes catastrophic forgetting, but at what cost? This isn't really a scalable solution. It's expensive in terms of memory. I have to maintain everything in some type of database, which, depending how long the lifetime of the learner is, could become potentially infeasible. It's also computationally expensive because whenever new data becomes available, I'm basically retraining on both old and new data. So this isn't really suitable for resource-constrained applications like embedded device learning and things like that. The other thing is that it raises privacy concerns. If I was doing incremental learning on medical data, there might be some type of privacy concern in place with storing all of that previous client information on a server somewhere. So maybe this isn't necessarily a solution for that reason. It also doesn't really match how humans and animals learn. It's highly unlikely that we have some memory buffer in our heads that is storing all of the information that we've seen throughout our lifetimes, and then when new data becomes available, mixing it together and just updating, right? The other two things at the bottom, maybe you do or don't care about them, but I think they're kind of interesting, right? We can't immediately recall new information. So this basically means, once new information becomes available, I have to wait now until my agent is actually updated on the old and new information before I can actually understand how well it understood the new information. The other thing is it's not doing transfer learning or transferring representations. If I learned some type of cat species in the past, and now I'm just learning a new cat species, maybe the fundamental features like 4 legs and fur or something like that haven't changed. So maybe I should be able to efficiently learn that new cat species just by, transferring some of the previous knowledge that the network once knew. So this brings me to why study continual learning. If you can just store everything in memory and continually update, then cumulative replay is the solution for you. But I argue that it's more interesting to think about continual learning, not just from what applications it can give us, but also from a basic research perspective. Right? We can answer questions like, how can we make more efficient learning algorithms? Maybe we don't want to do continual learning, or maybe some researcher doesn't want to do continual learning, but they should care because we can make more memory efficient and computationally efficient algorithms. How can we learn from very few examples? Things like this. The other thing is, how can we enable forward and backward knowledge transfer? This goes back to that example that I was just mentioning, where basically I have some feature representations for a previously learned category, and maybe now I'm learning something that's very similar. And it would be nice if I only needed a few examples of that new class in order to learn it, just because I can transfer knowledge from the past. But again, I mean, this also opens many new applications. I think Rupam mentioned one of these when he was introducing the talk. But one thing that's really exciting is things like on-device learning. You could imagine that maybe I have some type of robotic agent that's traveling around its environment and learning about various objects and classes. And we would be able to we would like to be able to do this on device and let it continually update. Other interesting applications include things like user personalization on smartphones or automatic speech recognition systems, right? Maybe I would like my agent to be able to adapt to the types of speech patterns that I use or keep current with current trends in the news, things like that. Recently, I think that there's been a lot of attention from some companies, specifically like Meta, on AR and VR applications, right? So we could consider how can continual learning be used to actually localize the coordinates of a user within their own home, right? This would provide them with a more personalized experience within their own home. So there's lots of interesting applications that continual learning could be used for. And beyond that, it also helps us develop more efficient learning algorithms. So specifically, I define the goal of continual learning as follows. We can train systems that accumulate and refine their knowledge over a lifetime from one or more domains in order to better imitate human learning. And as I mentioned before, the problems with this are if we do it in a naive way, we suffer from catastrophic forgetting of previous knowledge, where maybe the network learns new things very well, but it's not able to remember things that it once knew. And it would also be nice if we could make use of knowledge transfer in order to learn new things more efficiently, because they're so similar to things that we've learned in the past. Specifically, I'm going to outline what I consider to be the desired continual learning system. I know some researchers have differing opinions, but just so that we're all on the same page, I'm going to outline the criteria that I feel are very important. And this is what specifically I've been focused on throughout my PhD. So the first is the ability to learn and recall immediately from a single example. So basically, if my agent was provided with one new instance of a cat image, I would ideally like it to be able to update on that cat image, and then subsequently I could evaluate how well it learned that. I'm going to call this capability online continual learning or online streaming learning. The next capability is the ability to learn data in any order without catastrophic forgetting. So earlier I showed one end of the spectrum, which is basically learning data that's organized by class, right? I learned different bird categories one at a time. This is very difficult and arguably induces a lot of catastrophic forgetting because the agent's seeing such different tasks over time. But on the other end of the spectrum, maybe this isn't super realistic, and maybe I will revisit classes over time. And this could be closer to IID data streams, right? Where basically I take all of the data that the agent would receive and I can shuffle it, and I would still expect the agent to be able to perform well, even on that data stream. So I argue that it's important to test both of these capabilities because they kind of fall on two ends of the spectrum, right? A very difficult case where I'm going to induce a lot of forgetting, and maybe a case where I don't induce a lot of forgetting, but I would like my agent to be able to handle both of these extremes and anything in between. This is especially important because maybe the agent doesn't necessarily have control over the acquisition of the data from its environment, right? Maybe it's just, this is the stream I provided and I need it to update on that, and it doesn't necessarily have control over the order in which those inputs are presented. So the next thing is being able to learn using limited memory and compute overhead. I think I argued already a little bit for this, but this basically eliminates that cumulative replay solution, right? If I have some type of embedded device, maybe it has specific hardware constraints. I can't store everything. I can't just update on everything as it becomes available. So let's think about how to do this a little bit more intelligently. And then the final criteria I'm going to say is scaling to large scale, high dimensional problems. What I mean by this, large scale could mean high resolution images. It could mean hundreds to thousands of classes, millions of images. High dimensional problems could be requiring the agent to process multimodal input streams, right? Maybe I don't just have one input at every time step. Maybe I have both some audio and visual stream, and I need the agent to be able to process both of those and perhaps model the interaction between those components. So these are the specific criteria that I think a continual learning system should have. And this is what has kind of driven my research for the last couple of years. So now that I've given you kind of an overview of why we should care about continual learning and specifically the types of things I care about, let's talk a little bit about how the problem is typically set up for vision applications. So the first paradigm I'm going to talk about is called incremental batch learning. So in the incremental batch learning paradigm, we basically take a data set and we break it up into several batches. These batches could be defined based on classes, like I'm showing on the right? Batch A consists of images of cats, batch B consists of images of dogs, or batches could consist of several different classes or not be based on classes at all, right? It's however you want to define your task. But basically at each time step, the learner receives a batch of data from one or more classes. It can then spend time looping over the batch by shuffling it, just like traditional offline supervised learning. And then it's subsequently evaluated at the end of training on a batch. I argue that this training paradigm has some caveats. The first one being that it's slow. It's slow because I have to wait for a batch of data to accumulate before I can actually update. I have to wait for the agent then to loop through the data many times in order to actually learn about it. And then there's a delayed evaluation cycle, right? Instead of being able to immediately evaluate how well my agent learned a single image of a new cat, I basically now have to wait until it's finished looping through all of the cat images to understand how well it performed. Maybe I could test how well it's doing at the middle of an epoch or something like this, but this isn't necessarily how these systems are designed. So it makes the most sense to delay the evaluation until after a batch has been learned. And I think the more obvious thing is that it's just not reminiscent of how humans and animals learn. We don't sit here waiting to queue up a batch of data and then spend time batching through it, at least not during the waking stages of our lives, right? We're immediately rapidly learning new things and being able to make inferences based on those. So I argue that what we should really be studying is online continual or online streaming learning. And this is motivated by the natural world around us, how humans are constantly learning from temporal correlations, or even a robotic agent might be learning from video streams that have temporal correlations. So at each time step, the learner receives a single new example from its environment. It can then learn that example, and then it's subsequently evaluated after learning only that one new example. The additional criteria is that the learner is only allowed a single pass through the entire data set. This doesn't account for the case where maybe there's some type of auxiliary memory buffer being used, but then that has to factor into the amount of memory that the agent is actually using during the training stages. So the advantages of this paradigm are that it's closer to how we as humans and animals learn, and it's also better suited for real-time applications, right? I can immediately deploy the system, I can immediately understand how well it's learning about its environment, and it's very quick. In addition to these training paradigms, a lot of researchers, including myself, perform a pre-training phase before the continual learning actually happens. So a lot of us might be familiar with doing offline pre-training on something like ImageNet in order to give our neural network some type of initial feature representation, right? So I perform an offline supervised learning phase where I can train on the first and classes and examples, first batch of data in the data set, or even an alternative data set altogether before I actually perform the continual learning. And then when I perform continual learning, I can basically start from those pre-trained feature representations in order to continue updating them for new knowledge or just to use them as a pre-trained feature extractor. So that leads me to the first paper that I'm going to talk about today, which was published in a CVPR workshop in 2020, and it actually received the Best Paper Award at the workshop. So it's called Lifelong Machine Learning with Deep Streaming Linear Discriminant Analysis. I think there's a question.
Sorry, I was just wondering if this definition of continual learning handles concept drift, because it seems like there'd be a trade-off between when you want to forget things and when you don't.
Yeah, I mean, I think this is a really important question. So I agree that, certainly there are a lot of things that I, as a human, have forgotten over my lifetime that were not detrimental to my well-being, right? Like maybe I don't remember my high school chemistry class, and that hasn't been prohibitive of me conducting the rest of my life, but maybe if I needed to relearn chemistry, I could pick that up quickly again, based on having some prior knowledge. But I agree that this isn't really accounting for the case where maybe forgetting is okay. And I think that this is one of the things that needs to be discussed more, at least in the vision community, is when is it okay to forget? Because the way that the current training and testing paradigms for vision for continual learning are set up is basically how well can my agent perform on all previous data that it's ever seen throughout its lifetime. And that's basically the metric for performance. So I don't necessarily agree that that's the right way or the most realistic way to be doing things. I agree that maybe forgetting is okay, especially if it's something that's not you know, super critical to the agent's performance. So I guess to answer your question, no, it isn't really accounting for the forgetting being okay scenario, but I do think that that is something that we probably should be as a community thinking about more.
Okay, thank you.
Yeah, yeah, thank you.
May I elaborate on that question?
Yeah, go ahead.
What if the answer is different? That at one point, depression was defined as X, and a few years later, depression is defined as Y. So the same patient that was diagnosed as positive a year ago would have been negative now. So this isn't just additional information, this is just contradictory information.
Yeah, and that's actually a really important problem as well. So I think some folks have actually started studying exactly that problem in the object detection and semantic segmentation literature, because in that literature, typically we treat everything as background. So until I actually have learned a particular class, I treat everything else in the image as background. But then maybe later on in a subsequent training phase, I actually now have a label for that particular thing that was in the background previously. So now there's kind of like a shift in the label distribution. There are a couple methods looking at how to handle that, but I think that it's still an open question, and I still think it's really something important. It could also be related to something like, you know, maybe at some point I learned what dog was, but later on I learned different types of dogs, and I would like to, you know, refine my knowledge even further. I think that those are important questions as well that are also, you know, important to study, but maybe are a little bit understudied, except for maybe object detection and semantic segmentation to some extent. Yeah.
Thank you.
Thank you for the interesting questions. I see another one. Yeah. Also contradiction. Yeah, contradiction in terms of what Matt is mentioning in the chat. Yeah, awesome. So this brings me to this first paper that I want to talk about. So before we were talking a little bit about what would happen if I perform this pre-training phase to initialize my feature representations before actually performing continual learning. So my question is, if we perform a pre-training phase, how good are those features for a downstream application like continual learning? If the features are already pretty good, then could we just train the output layer of a neural network instead of actually having to update the feature representations? This obviously has its own pros and cons, but that was kind of the motivation for this paper. So in order to study this question, we revisited the streaming linear discriminant analysis model that's been commonly used in the data mining community. So if you're not familiar with how streaming linear discriminant analysis works, it works in the following way. First, I pre-train some type of feature extractor, maybe a convolutional neural network on some data set, and then I can push an image through it to extract an image feature. Based on those image features, the LDA model then stores one running mean vector per class and a shared class covariance matrix among all of the classes. At test time, given a new image feature, I can then compare it to Gaussians in the feature space that are defined using these running class means and shared covariance matrix. And based on the Gaussian that my test image is close, or test feature is closest to, I can then assign that label before making a prediction. So before I show the results, I'm going to use these two data sets a couple of times throughout the presentation. So I just want to make sure that we're all on the same page. So I think a lot of us are probably familiar with the ImageNet 1K data set. It consists of high resolution images from 1,000 classes. And I really use this data set in order to test the ability of models to scale, right? It has hundreds of classes, or 1,000 classes with hundreds of images each, and it has over 1 million images in total. But the problem with ImageNet is that all of the images are just static, right? There's no temporal correlation between one frame to the next. They're basically just all independent from one another. So in order to really understand how well these incremental learning algorithms actually work on video-based data sets, I use Core 50. So Core 50, I'm showing a GIF of at the bottom of the page. It basically consists of videos of a person moving these household objects around with their hand. So it has 10 different classes, which are shown in the columns, things like, cell phone, scissors, light bulbs, things like that. And then across the rows, you can see that there's different object instances for each of these classes, right? So I have cell phone number 1, cell phone number 2, scissors number 1, scissors number 2, things like this. And the reason for using this data set is basically to test how well the models can handle temporal correlations in non-IID data streams. So I mentioned much earlier that I was very interested in studying these different data ordering scenarios. I think a lot of the community has been focused on class incremental learning, but let's also study additional data orderings to understand how robust our algorithms are. So the first thing would just basically be IID. Let's take the entire data set, core 50, and just shuffle all of the frames and then learn them one at a time. This should arguably be the easiest case for a neural network. Stochastic gradient descent assumes that we shuffle all of our data and then learn it in a shuffled way. The next data ordering is class IID, where basically I take all of the videos and I organize them by which class they belong to, but then I shuffle the frames within the class. The reason for doing this is because on data sets like ImageNet, all of the images are independent from one another. So shuffling within class is kind of mimicking that class incremental learning setup on static image data sets like ImageNet. The last two orderings are what I argue the most realistic, right? So the first one is called instance, where basically I take a video of a particular object instance and I present that to the learner in the order in which it was collected, but maybe I can revisit classes, right? So maybe I learn about PopCan number 1 before learning about mug number 1, before learning about PopCan number 2, and so on. So this is kind of resembling the human experience where I learn things in a temporally correlated order, but maybe I can still revisit previous classes. And the final data ordering is class instance. So this is kind of a hybrid of class IID and instance, where I basically organize videos based on the class they belong to, but then they're viewed in the temporal order in which they were collected. So class IID and class instance are probably arguably the hardest in terms of catastrophic forgetting for agents, but it's also important to study these additional data orderings like IID and instance as well. So first I'm going to present the results on the ImageNet 1K dataset on the right. All of the models are using a ResNet 18 pre-trained feature extractor on only 100 classes from ImageNet. I just want to point out I am not pre-training it on 1,000 classes of ImageNet and then saying, please learn 1,000 classes of ImageNet. But this is common in computer vision literature. And then basically, what I really want to draw your attention to is this iCarl and end-to-end model. So iCarl is in orange and end-to-end is in pink. But those models are trained in that incremental batch learning setting. So basically, they're given 100 classes worth of data. They can spend time shuffling through it and looping over it before being evaluated after it's learned 100 classes. Whereas our SLDA algorithm is only updating on one example at a time, right? And it doesn't really have many memory requirements besides its covariance matrix that's shared among all of the classes. So on the right, I'm basically showing the top 5 accuracy of all of these methods after being trained on a specific number of classes all the way up through all 1,000 classes in ImageNet. And what's really interesting is SLDA actually achieves the highest performance at the final time step, and it actually outperforms this iCarl batch model at every increment during training. This was pretty cool because since SLDA is only updating one sample at a time, it ran over 100 times faster and used 1,000 times less memory than iCarl and end-to-end. So, not only does it achieve moderate performance, it's also significantly faster and more computationally efficient. So we also studied how robust the method was to these different data ordering scenarios. Note that this iCarl method I was just talking about is specifically designed to work in the class incremental learning scenario, and without modifications, cannot really handle revisiting classes. So that's why you only see that bar in these 2 class orderings. But overall, what we can see is across all 4 of those data ordering scenarios I talked about, SLDA achieves the highest performance independent of if I kept its covariance matrix fixed or plastic after some initial training period. So this was kind of interesting. The other interesting thing to note here is that, as expected, all of the methods performed the best on the IID data ordering and had the most trouble with the class orderings, right? Those are inducing the most amount of forgetting, whereas IID isn't inducing as much forgetting. So, SLDA has its own pros and cons. As I showed, it's provably order agnostic. It can learn incredibly fast, which makes it well suited for embedded device learning, where we actually care about memory and compute constraints. But you might be asking yourself, oh, it can't do any representation learning, right? It's reliant on this fixed feature representation network, which I'll talk about in just a little bit. But since this algorithm is quite suitable for embedded device learning, we wanted to study this further. So we actually just received acceptance of this paper this week to the Conference on Lifelong Learning Agents, but we were actually studying online continual learning for embedded device applications. So an embedded device is basically a device that is purposefully built for a particular application, right? We can think about things like VR or AR headsets or even a mobile device. They're typically constrained in terms of the amount of compute and memory that they have available to a user. So these are important things that we need to take into consideration when studying continual learning. So the motivation for this paper was basically, how can we develop continual learners that are able to perform well in a limited memory and compute environment? And what other factors are important when actually studying continual embedded device learning, right? So on the right, I'm showing you some of the factors that we evaluated in this paper. We tested how well methods could actually perform when they were subject to scale, right? So again, learning hundreds of classes, potentially with millions of examples. How well they could perform in the face of imbalance. What happens if one of my classes has a lot of images and another class only has a few images? What happens if I'm learning from temporally correlated video streams? What happens if the agent is learning in a low shot learning setting, right? So basically, if it's only provided with a few examples of a new class, how well can it generalize to other instances from that same class that maybe it hasn't seen before? And then obviously memory and compute. So we performed a comprehensive study using these factors to kind of guide the types of experiments we were running. And we pre-trained all of the CNNs on the ImageNet 1K dataset. And we studied both the SLDA algorithm that I just talked about, as well as 6 other lightweight algorithms that could update only the output layer of the CNN. So again, this work was focused on that, using a fixed feature extractor and only updating the output layer of a neural network. So we studied 7 different methods. We studied just fine-tuning the output layer using an online multi-class perceptron, a streaming one verse rest classifier that basically considered the distance of a sample to the closest means in feature space, but also how far away it was from other class means, the nearest class mean classifier that's very common in continual learning, Gaussian naive Bayes, streaming linear discriminant analysis, and then basically a simple replay algorithm that either stored 2 examples per class to be in a similar amount of memory usage as these other algorithms, as well as one that stored 20 samples per class. And we studied 5 different backbone architectures. So ResNet 18 is actually kind of the standard in continual learning literature. A lot of people are just using a ResNet 18 convolutional neural network, but we were also interested in studying additional, more computationally efficient CNNs like MobileNet v3 and 2 versions of the EfficientNet. So first, we asked the question, how does the CNN choice actually affect performance? So these are some results on another video-based data set. And I've basically, on the left, taken the average of all of the methods that I just showed on the previous slide for each of the different backbone architectures. And what's interesting is, you know, a lot of us are just using ResNet 18 to actually perform continual learning, but it's actually the network that had the lowest performance across methods. It's more interesting that, you know, these efficient nets were actually achieving much better performance than ResNet. This is interesting as well because not only are they performing better, but they also require fewer computational resources. They take up less memory. They're more computationally efficient to actually, you know, push the images through and get a feature representation. So from this, we found that architecture choice has a large impact on certain algorithms like naive Bayes and streaming one verse rest, but replay and SLDA were actually a little bit more robust. You can see on the right here, I'm showing you the performance of each algorithm when using an efficient net B1 backbone versus using ResNet 18, right? And methods like SLDA and replay actually had quite a small gap between the performance on the 2 networks, but some methods like naive Bayes actually are quite dependent on, you know, the feature representations that are being given to it. So this was kind of an interesting finding. Here I've actually summarized the results of those different methods that we studied across those various factors that I mentioned much earlier. If you're interested in more specific results, I'll point you to the paper because we have a lot of tables and plots there. But basically I'm showing you these radar charts, which are basically measuring the performance of these learners across 5 different axes, and then we draw a polygon, and those polygons that have the most area in them are said to have performed the best. So this omega metric is measuring classification efficacy, the compute and memory requirements of an agent. Video is testing how well the methods perform on video data sets, low shot and low shot settings, how well they scale and how well they perform in the face of imbalance. What you can see is that overall, both SLDA and replay with 20 per class performed quite well, right? They achieved the highest overall performance, but it is interesting to look at, when some of these other methods performed well, right? Like fine tune performed well on videos, but maybe it didn't have the best performance when it was required to scale up to these large scale data streams. So overall, what we found is, SLDA and replay works the best. If you want to use even less memory, you can probably use the nearest class mean classifier as well. And we're trying to argue that the efficient net backbone, yielded better results and it's more computationally efficient. So maybe the community should also be considering additional types of convolutional neural network architectures. But the biggest thing about this work and the SLDA work is that they were relying on fixed feature representations, right? And you might be asking yourself, well, if I'm doing continual learning, it would be really great if I could also update my feature representations to be representative of new classes. And so to do this, typically people use experience replay. So maybe they store either a subset or, all of the previous data in some type of memory buffer, or they can use a generator. Right down here, we can see we're storing old images of penguins and jellyfish and things like this. And then as new data from the environment becomes available, I can mix the old data with the new data to update the network in order to overcome the forgetting problem. But storing raw pixel images in a buffer is quite memory intensive, depending how many of those images you want to store, and it's not really biologically plausible. It's not really likely that we're storing raw pixel representations in a memory buffer to actually perform learning. So this leads me to a paper that we published in ECCV 2020 called Remind Your Neural Network to Prevent Catastrophic Forgetting. So the motivation for Remind is that humans and other animals learn by storing compressed representations of temporally correlated experiences in our hippocampus. We're not storing raw experiences, we're storing compressed representations. And typically these representations are from higher in the visual processing hierarchy, right? If I had something like a convolutional neural network, this would mean grabbing a feature from somewhere in the middle of the network and storing that instead of storing just a raw pixel representation. When humans go to sleep at night, these representations then get consolidated from the hippocampus over to the neocortex. So the Remind architecture is actually inspired by these two theories I'm mentioning on the previous slide. The first is called hippocampal indexing theory, and the second is called complementary learning systems theory. So we were taking kind of a neuroscientific approach to developing this architecture. So the two key ideas for Remind are first to store intermediate representations in a compressed manner for fast learning. So like I mentioned before, if I have a convolutional neural network, this means I'm going to extract features from somewhere in the middle of the neural network and store those in a compressed way in a memory buffer. And then when I want to actually train some of the representation learning layers of my network, I can reactivate or reconstruct those compressed representations and replay them in order to learn and acquire new information or new knowledge. So specifically, Remind works in the following way. I can basically take a new input, which I'm showing here in red. I can push it through some frozen layers of a neural network. Maybe these were initialized during some pre-training phase, but notice that it's just a few layers instead of the whole neural network like SLDA. I can then extract some type of feature map, and then I can use some type of compression or quantization algorithm. In this paper, we used product quantization in order to compress that representation to store it in a memory buffer. Here you can see I store the new memory. I then reactivate some old memories using random selection. I mix them together, I push them through the decoder to reconstruct them back in feature space, and then I can train the plastic layers of my neural network. Again, we compared how well Remind worked on the ImageNet dataset. So on the left, I'm basically showing you how well these incremental batch learning methods like the iCarl you saw earlier and more recent methods like Unified and BIC, how well they performed when they ran in their traditional batch learning paradigm versus how well they worked when they were required to run in the streaming paradigm. And so what you can see is in the batch learning paradigm, we're slightly below the state of the art, maybe by less than 2%. But when we move over to the streaming paradigm, our method is still able to perform quite well, whereas even the best method, Unified, drops by nearly 20%, right? So just by switching the paradigm of training in batches versus training in an online learning setting actually makes that performance drop quite significantly. On the right, I'm again showing you a learning curve of how well these methods performed over time when trained in the streaming setting. And so what you can see is that Remind it outperforms the other methods. But what's interesting is the next best performing method was our SLDA method. So this kind of shows to some extent the impact of using replay and the impact of updating feature representations, right? So it does actually bias some performance improvement. Remind is also order agnostic. So similar to the SLDA model that we tested on those 4 orderings of core 50, we again tested this remind method on those 4 orderings, this IID, class IID, instance, and class instance. And what you can see is that it worked pretty well regardless of the data ordering. So again, it's robust to the order in which the data is appearing. I see a question. Yes, so streaming LDA can handle an increasing number of classes over time. Basically, in order to learn a new class, I would just initialize a new mean vector and then continue updating that mean vector. So yes, it can handle new classes over time. Great. So the coolest thing about Remind is that, it's not bespoke to a specific task, right? It's more of this idea of compressing high-level feature representations and then just training like the later layers of a neural network. So it can actually be used for multiple other applications. And in fact, we tested how well it worked for 2 applications, visual question answering and object detection. So if you're not familiar with visual question answering, it basically provides an agent with a natural language question and about an image, right? And then the agent's goal is to answer that natural language question about the image. It requires many types of vision tasks, right? It could require counting if the question is asking how many of something there are in the image, identifying different types of attributes, classifying the type of scene, or even doing things like color attribute detection, right? So this requires many different types of capabilities. At each time step, we give the agent an image with an associated question, and then the output needs to be the correct answer to the question. Since I mentioned earlier that I'm very interested in these data ordering scenarios, we studied 2 data orderings for this particular task. The first is just IID, where I randomly shuffled the entire data stream, and the other was taking advantage of this actual domain by organizing the stream by question type, right? So you could think of these things up here, counting, attribute detection, as question types. So maybe first my agent learns about counting, then it has to learn about scene classification and things like this. I'm just presenting the results on one data set here. So the Clever data set is commonly used for VQA, a test for multi-step compositional reasoning. You can see an example on the left. Are there an equal number of large things in metal spheres? So first the agent would be required to identify how many large things are in the image, how many metal spheres are in the image, and then reason about if there are an equal number of those. So what's most interesting, I think, is when we were studying this, I thought the IID data ordering would be the easiest for all of the methods. And in fact, it is the easiest except for Remind, right? So we can see this fine-tune, extreme, and SLDA method actually performed quite well on IID, but Remind had much better performance on the question type ordering. This was kind of interesting, and it makes us wonder if there's some type of optimal curriculum for learning these tasks that might be beneficial to Remind's learning. The other thing I mentioned is that we studied this for object detection. So this was in a separate paper, which was published in BMVC 2020. But basically, we made this new algorithm called Rodeo, which basically uses these similar concepts as Remind to compress these high-level feature representations in a memory buffer. And what you can see is that it had the best performance overall. But what's interesting is we also made a streaming SLDA plus regression model based on our SLDA work, which also had moderate classification and object detection performance while using significantly fewer resources. So this just kind of shows that we were able to extend these works beyond just image classification. So again, all of these things are based on using pre-trained features to some extent. Maybe Remind only uses them at the beginning of the network and then updates feature representations later in the network, but we were interested to see how just swapping out supervised feature representations for self-supervised feature representations could improve performance. And so we published this in a BMVC paper in 2021. So basically, self-supervised learning trains a system without the need for human annotated labels, right? It basically makes these pretext tasks for a network, and then uses those as a supervision signal for the network, right? So maybe we could use something like rotation, where we rotate an image by a fixed amount, and then we know the amount in which we rotated it, so we could use that as a supervision signal. More recently, a lot of people have been using data augmentation for self-supervised learning, right? Where basically we augment an image a bunch, and then the network must learn to bring images that have been the same image that's been augmented multiple ways together, and then push it apart from images that are from different classes. So we compared the performance of Remind on ImageNet when using features that were pre-trained using supervised learning versus self-supervised learning. And so what we found on the left, I'm basically showing you the % increase over using supervised features with the Remind method and using different numbers of pre-trained classes. So Barlow Twins, Moco V2, and Suave are 3 recent self-supervised learning methods. And what you can see is that all of these methods had improved performance over just using supervised features. And the performance gains were actually quite significant when we looked at using a fewer number of pre-trained classes. This is desirable because then we don't have to label, or well, it's desirable because we don't need as much data, right? If I only need to learn from 10 classes, this is much more efficient than having to learn from 100. On the right, I'm basically showing you that same learning curve on ImageNet that I showed earlier. In orange is the performance of Remind that I showed you just a few minutes ago using supervised features, and the blue is basically if I just swap those features out for these Suave self-supervised features, and it actually gave us nearly a 15% performance improvement. So I know that this has been a lot of information, but just to kind of summarize what I talked about today, online continual learning can be used for so many new applications like on-device learning. We can have immediate updates with immediate inferences being made. We don't have to worry as much about external data processing if we're considering these memory and compute requirements. I showed you several online continual learning systems that all learn from streaming data. They can operate in different data ordering scenarios, and they have limited memory and compute overhead. So just to kind of finish up, I want to give a little bit of my insight into what I think is next for the continual learning field. So the first thing is continual learning with limited labels, right? The natural world around us is providing us with an abundance of data, but it's all unlabeled, and getting labeled data can be costly and time consuming for humans, right? So there's 2 ways we could deal with this. The first would be to use active learning in order to let the agent just select the most informative subset of that unlabeled set to be labeled, right? So this is reducing the amount of labels I need to acquire. And the other thing would be to use self or semi-supervised updates in order to perform representation learning on this abundance of unlabeled data, right? So I can still make use of that in some sense, but maybe I don't need to do this expensive thing of getting the labels. So that's one direction I think is really interesting. The next interesting direction I think is doing multimodal continual learning. And we kind of did this when we studied visual question answering, right? Because we were handling both a natural language question about an image, but there's a lot of other types of modes we could think about, right? We as humans have different senses. We have touch, we have sight, we have hearing. Agents often have multiple sensors, right? Maybe we have a camera, maybe we have a depth sensor, maybe we have some type of touch sensor, things like this. So I think it would be really interesting to develop continual learners that can fuse these data sources together. This could be particularly important for things like if I have a video stream with audio and then the video cuts out, maybe my agent then needs to learn to rely on the audio stream. Another thing is open world learning. So open world learning is basically an extension of continual learning that basically additionally requires agents to identify samples that are unknown, right? So maybe it learned about something in its training set, but now it gets a new object and it has to say, I don't know what that is, and then subsequently learn it. So I think this is also a really exciting next direction. And finally, yeah, I think, you know, some biological inspiration for continual learning. We as humans do this very well, right? We're learning a lot of new things throughout our lifetime. We're not catastrophically forgetting things that are important for us in order to conduct our daily lives. So there's a lot of future work that could take inspiration from this, things like Hebbian and error-driven learning mechanisms, using generative models instead of actually storing raw samples in a replay buffer, and a lot of other things like this. If you are very interested in this, I'll point you to this recent review that we wrote with some neuroscience collaborators who talk a lot about how this is done from the neuroscience perspective as well. So that was kind of a fun work. So I obviously none of this work was not done alone. It took a team of us to do it. So I want to acknowledge all of my co-authors and the people who funded the research. So thank you very much for listening, and I'm happy to answer any additional questions.
Wonderful, Taylor. Thank you so much. So the floor is open for discussions. Please feel free to unmute yourselves and ask questions directly to Taylor.
Oh, I see one in the chat. Oh, clap. Thank you.
I guess I have a question. This is very interesting stuff. And I feel like a lot of the time, the thing that you mentioned last about biological connections is always so intriguing. And I feel like we all feel like that there's all these insights on the neuroscience side, and our understanding of how humans learn should really help us do a better job. So could you tell us maybe just one thing that you realized after writing that paper with some neuroscientists?
Sure. Yeah. I mean, I think that we're doing this a lot differently probably than how we as humans are doing it. And I think to some extent we aren't necessarily, I mean, I think a lot of continual learning research isn't necessarily driven from the biological perspective. It's more driven from the machine learning perspective of understanding, you know, what's happening to my features? Why is there this drift happening? Why is the forgetting happening? But I do think it's interesting to consider some of the neuroscience perspectives, right? Like a lot of unsupervised or Hebbian type updates, right? Like local update rules that are using not necessarily a supervision signal. We as humans are, you know, I can learn a lot about looking at objects without actually having to understand what it physically means. So I think that there's a lot of inspiration to be taken from that. Yeah, I guess that's kind of my thought. We have a whole section in that paper talking about various ways that this could be incorporated. I think that only brushes the surface of, you know, biological inspiration that could be taken. So yeah, I think that's an important next step.
In case, I mean, someone else might want to ask a question, but I guess I'll just ask one more. I mean, I thought a little bit about local updates in a network. And in some sense, that shouldn't really solve the problem, because as time passes, your local updates should still start, hopefully help you do well for things you've done recently, and presumably overwrite whatever things you learned in the past. So how is it that Hebbian learning could help us with this problem?
Yeah, I don't necessarily know that Hebbian learning would solve the forgetting problem, but maybe it might help make, you know, maybe it might make different or more informed updates just locally without having to use as much supervision, I guess, right? Because Hebbian learning doesn't necessarily have a supervised learning signal like cross entropy loss requires. So I think just from a more efficient perspective in that way of not having to worry about getting labeled data. But yeah, it certainly could still suffer from the forgetting problem and overwriting of previous representations. So how to do that is still kind of an open question, I think. Yeah.
So I guess I have a question, comment. You didn't talk about predictions. You talked about self-supervised learning and semi-supervised learning, but I like to think about prediction learning, because prediction learning, then it's clear that you have sort of like do have a plentiful source of labels, which are, you have your temporal stream of experience, and if you're trying to predict from one things that are happening, what future things will happen, then you get labels because you find out what did happen. And so I just wonder, yeah, do you not, are you just lumping that into semi-supervised learning?
Yeah, so in terms of, you mean getting a supervision from the local environment itself instead of an actual label, like physical label, like using the environment itself as the supervision for a task?
If the task is prediction, then you do get the correct label from the data.
Okay.
So prediction means something special to me. I don't mean like supervised learning involves prediction. I don't get, it doesn't count as prediction because it's not saying something about the future. But if you're trying to predict a future event, and then you see, of course, then you will see the future event when it eventually becomes the present. And so you have labels, an infinite supply of labels, and labels are then plentiful.
Okay.
So you're yeah. So I guess it's you're really haven't thought too much about that. So maybe we can talk some more about that, because I think it's actually a very productive future direction for the field to move in.
Yeah, I think to answer your question, I have not thought about it in terms of that actual setup. I guess this is sort of similar to auto-regressive type updates. Is that, yeah. So I guess I haven't thought about this much, but I do think that is an interesting direction, because you could use that as the supervision itself for learning a robust feature representation. Yeah, I apologize, I don't have a good response to that, but I do think auto-regressive self-supervision for continual learning could be an interesting next step. Yeah, I appreciate your thoughts on that as well.
Cool, thanks. Let me just follow up that I really enjoyed your presentation, and I really enjoyed the care with which you're trying to phrase the issues and answer them, and with respect for all the previous work that's been done and the different points of view that people take. It just seems like very carefully work that's going somewhere. So thank you very much for your presentation today.
Thank you. I really appreciate that. I've tried really hard during my PhD to try to put my work in the context of what others have done. Yeah, thank you. I see one in the chat. Is it trivial to extend all of this to the regression setting? I mean, I guess in some sense, some of these things probably could be extended to regression quite easily, like remind, right? When we did object detection has a localization component, which is regression. And, you know, the same concepts from the classification setting actually applied quite well there. In terms of, you know, we also made for the object detection case an SLDA plus streaming regression model, and the streaming regression model kind of updated in the same way. It had running means and running covariance matrices, and in that sense, it was still operating in the same sense. I think we still have the same types of problems that we might need to pay attention to, right? Like forgetting, and what robust feature representations could we have for making sure that we output the correct predictions. But yeah, I think a lot of this could probably be extended to regression. Beyond object detection, I myself have not studied regression too much, but I think some of the general concepts could be applied in that setting as well. Yeah. Thanks.
Any other questions? Wonderful. So if not, let's thanks Tyler for a wonderful presentation and engaging discussion. I think Tyler, you are scheduled to meet other people later today. So thank you so much for presenting today. And thank you everyone for joining in. We'll see you next week. Next week is AI week. Russ, you want to talk something?
Maybe just remind people that AI week is next week, and it's a major event. It's 4 days of exciting things happening, lots of presentations by people like Rich, as well as Martha and many others. Everyone should come. If you want information about that, ask, go to aiweek.ca to find more information.
AI-week, and it really is going to be awesome. There's like 1,000 people coming from outside, and we're going to hear from them and learn from them. And it's a big thing. And they have their own beer. They have an Amy beer. We have to get into that.
Sure. I have put the link in the chat box. Feel free to copy it and maybe bookmark it to know about the events.
Yes.
Thank you so much.
Cool.
See you at the AI week. Bye.
Thank you again for inviting me. If people have additional questions, feel free to email me as well.
Sure. Wonderful. Thanks.
Thank you, Tyler.